Hey guys, so today we're going to be looking at 4.3, which is going to talk about particle motion again, and it's going to talk about numerical style problems. So we're going to use some of the derivative rules that we know, some other things that we know, and apply it to particle motion. So position, velocity, acceleration. So the data in the table below gives selected values for the velocity in meters per minute of a particle moving along the x-axis. The velocity v is a differentiable function of time t. So, A, at time t equals 0, is the particle moving to the right or to the left? Explain your answer. So remember, it is moving to the right if our velocity is positive, and it's moving to the left if our velocity is negative. So if I look at my table right here, at t is equal to 0, my velocity, v of t, is equal to -3. So, and I'm actually going to type this so you guys can actually read it. What that means for us is that the particle is moving to the left because the velocity at time t equal to 0 is negative. So that would be explaining our answer. It's moving to the left because our velocity is negative. All right, let's look at part B. So is there a time during the time interval 0 to 12 where the particle is at rest? Explain your answer. So to answer this, we are going to use our intermediate value theorem. I know it's been a while, but we are going to use the intermediate value theorem. So for the intermediate value theorem, we need to say that it's continuous. So it's telling us that the velocity v is differentiable. So if it's differentiable, that means it is continuous. So once again, I'm going to type just so you guys can read it a little bit better. So v of t is differentiable. Oh, I cannot spell. Therefore, it is also continuous. So that's the first part. We need to say that it's continuous. And we're going to say specifically that it's continuous on interval from 0 to 12. So I'm going to say that it's continuous on that interval specifically because that's the interval that we're looking at. And since it's continuous, that means the intermediate value theorem guarantees a value, let's say c, or instead of a value, let's say a time c on our interval 0 to 12, such that v of t, v of c is equal to 0 because, and the reason that we can say this is because if we look up here on our table, at 0 we have a negative velocity, and at 12 we have a positive velocity. So because it is continuous, that means it has to cross our axis at some point. It has to cross that 0 at some point. So what I'm going to say is that it guarantees a time such that v of c is equal to 0 because v of 0 is less than 0, which is less than v of 12, which that's what we just talked about. Our v of 0 is -3, and that's less than 0, which is less than our v of 12, which is 5. So there's part B. Let's look at part C. So this one says, use the data from the table to find an approximation for v prime of 10 and explain the meaning in terms of the motion of the particle. So show your computations that lead to your answer and indicate units of measure. So if we're finding an approximation for v prime of 10, that means I'm going to do that rate of change formula. That's our average rate of change right there for our velocity. And if we're looking at 10, I'm going to do between 8 and 12. So I'm going to have v of 12 minus v of 8 over 12 minus 8. Well, v of 12 is 5 minus v of 8 is 7 over, well, 12 minus 8 is 4. So I'm looking at a -2 over 4, which gives me a -1/2. So this means that my v prime of 10 is equal to -1/2. And if our velocity is meters per minute, this is going to be meters per minutes squared. And the minutes is the part that's squared. And what does this mean in terms of our situation that we're looking at, in terms of our problem that we're looking at? So once again, I'm going to switch over to typing so you can read it a little bit better. What this means is that, well, if we're talking about position, velocity, acceleration, the derivative of velocity is acceleration. So in terms of the motion of our particle, this means that the acceleration is a -1/2 meters per minutes squared. Let's just do meters per square minutes. So what this means is our acceleration is negative. Our particle, with our acceleration being negative and the velocity being positive, and we can know that the velocity is positive because it has to be between 7 and 5, which are both positive numbers. What this means is that our particle is slowing down. And the reason that it's slowing down is because the acceleration is negative and the velocity is positive. So we can type that out in a sentence right here. So the acceleration is -1/2 meters per square minute, and the velocity is positive. Thus, our particle is slowing down. So there's your explanation there. So these problems are, once you have the number, you kind of have to explain what's happening with it. So I'm sure you guys can find the number pretty easily. It's going to be this explanation that you're going to have to think a little bit more about. All right, let's look at number 2. So this one says, Ben rides a unicycle back and forth along a straight east-west track. The twice differentiable function b models Ben's position on the track, measured in meters from the western end of the track at time t, measured in seconds, from the start of the ride. So the table gives values for b of t and Ben's velocity, v of t, measured in meters per second at select times t. Use the data in the table to approximate Ben's acceleration at the time t is equal to 5 seconds. So if we're talking about approximating an acceleration, that means that we are going to use our average rate of change here. And we're looking for at the time t is equal to 5. So I'm going to do between 0 and 10 right here. So if I'm approximating Ben's acceleration, that means that I'm going to be looking at the velocity at 10 minus the velocity at 0 over 10 minus 0. So my velocity at 10 is 2.3 minus my velocity at 0, which is 2.0, over 10 minus 0 is 10. So I'm looking at a 0.3 divided by 10. So what that's going to give me is 0.03, and we're talking about acceleration, so it's going to be meters per seconds squared. So there's our answer for part A. Let's look at part B. So I've got the same problem up here. So for part B, it says for 0 less than or equal to t less than or equal to 60, must there be a time t when Ben's velocity is 2 meters per second? Justify your answer. So once again, we are going to use our intermediate value theorem here. Intermediate value theorem. So the first thing is we have to verify that the velocity is continuous. And so it tells us up here the twice differentiable function b models his position. So if that's differentiable, then it means that we've got the velocity. And then it says it's twice differentiable, so we also have an acceleration, which means our velocity is differentiable, which means our velocity is continuous, because it can't be differentiable if it's not continuous. So I can come down here, and I'm going to scroll down a little bit, and I can say that v of t is differentiable thus it is continuous on our interval, and this time we are looking from 0 to 60. So the intermediate values theorem guarantees a value c, or let's not say value, let's say a time c on our interval 0 to 60, such that we're going to say v of c is equal to 2 because, and here's where we got to double check and make sure that all of our numbers line up. So if we're going from 0 to 60, at 0 our velocity is 2 meters per second. And if we're looking up here at 60, our velocity is 4.6 meters per second. Well, we already know that at 0, the velocity is 2 meters per second. So that kind of just guarantees that right there, right? So what I'm going to say is because v of 0 is equal to 2, which is less than my v of 60. And there we go. That's it for part B. Let's look at part C. This one's going to be the fun one. This one's going to take a little bit longer because we are going to have to do some related rates here. So it says a light is directly above the western end of the track. Ben rides so that his time t, the distance L of t between Ben and the light, satisfies this equation right here. At what rate is the distance between Ben and the light changing at the time t is equal to 40? Include units in your answer. So let's kind of look at this right here. I've got this equation right here. So let's go ahead and take our derivative with respect to t right here. But instead of L of t, I'm just going to say L squared is equal to 12 squared plus B squared. So we can write it a little simpler there without all of the t's. So when we take our derivative, the derivative of L squared, I'm going to bring down that 2. So I'm going to have 2L dl dt is equal to, well, if I have 12 squared, that's just going to become a 0. And then over here, that 2 is going to come down, and it's going to be 2b db dt. So at what rate is the distance between Ben and the light changing at the time t is equal to 40? So if we're talking about t is equal to 40, we're looking at this right here. So if I'm looking at all of my variables that I need to figure out what they are, I need to figure out what L is. I need to figure out what B is and what dB of dt is. And then what I'm looking for is dL dt. At what rate is the distance between Ben and the light changing? So I can get B and dB dt from my table right here. B is going to be equal to 9, and dB dt, the derivative of B, is going to be that 2.5. What I'm missing that I still need to find is my L. So to find that L, I'm actually going to use this equation right here. So I know that L of t squared is equal to 12 squared plus B of t squared. Ooh, that's a 2. There we go. So I'm going to say L squared is equal to, well, 12 squared is 144 plus, well, B of t is 9, so 9 squared. So L squared is equal to 144 plus 81. So L squared is equal to, well, 144 plus 81 is 225. And when I take the square root of both sides, that gives me that L is equal to 15. So now I've got a 15 that I can plug in here. So let's plug in all of those values. So 2 times 15 dL dt is equal to, I don't need that 0, so I'm going to say 2 times my B, which is 9, times my dB dt, which is 2.5. So I'm going to have 30 dL dt is equal to, well, 2 times 9 is 18 times 2.5. And then all I have to do is divide both sides by 30. So dl over dt is equal to 18 times 2.5 divided by 30. So 18 times 2.5 is going to give us 45 over 30. And I can simplify that to dl over dt is equal to, well, I can divide both of those by 15, so I have 3 over 2. And I need to make sure that I have my units. So this is going to be meters per second because it's the rate of change between the distance between Ben and the light. So dLdt is that 3/2 meters per second. All right, that is it for the set of notes. You guys do have a Go formative for homework that you need to work on. And remember, if you have any questions, you guys can always come to my tutoring times or ask me during class. And you guys go ahead and get started working on that Go formative.